Welcome to the next video in linear models. This is video 4 on the covariance of two vectors, and this is chapter 1, section 1 at the very end. So to start with, we're going to give a definition for the covariance of some two random vectors, and they don't even have to be the same length, right? R could have length, W could be a random vector of length R, Y could be a random vector of length S. Let's go ahead and use the notation that the expected value of W is this gamma, the expected value of Y is mu. And then the definition of the covariance of these two random variables, vectors of random variables, is the expectation of this thing, that is the product, the matrix product, between this column vector and this row vector. So go ahead on your own and work out that when you do the product of a column vector by a row vector, what you get, especially with these dimensions, is an R by S matrix. So this is the expected value of a matrix, and so it is, the matrix that is filled with all of the individual expected values. Now, I'm going to go ahead and mention that a quick consequence of all of these definitions is that we can take the covariance of AWBY and show that it is equal to this thing down here, A covariance WY times B prime, B transpose, right? Okay, let's work that out real quick. Immediately by definition, this is just what the covariance is, although I have computed a little bit here, right? This is the expected value of AW, right? And since the expected value of W is gamma, then I have A gamma there. The expected value of BY is this B mu, and so we're going to compute this product in some sense. And in particular, let's go ahead and take the transpose of this matrix. I'm also factoring out A. Actually, let's start there. I am taking the matrix A and moving it outside to the left. I'm also taking the matrix B here and moving it outside to the left, but then I'm taking the transpose, so what I get is B transpose on the right times everything else transpose. Okay. A is a constant matrix. It can move to the outside on the left. B prime is also a constant matrix. It can move outside. What is left over turns into the covariance of W and Y, and there's the proof. Okay, so that one was relatively short. We're going to get into a significantly longer proof here. And it is going to be a proof of the fact that if we have any appropriately sized matrices, constant matrices A and B, with random vectors W and Y, then the covariance of AW plus BY is given by the following formula. Now, it's this long and somewhat ugly formula, but it basically says that if you just take the W part, right, you get A on the left and A prime on the right. Somehow that makes perhaps a bit of intuitive sense, and then you somewhat symmetrically get the Y part, and you get B on the left, B prime on the right. Okay, then you get A on the left, B prime on the right with the covariance of WY in between. Not sure I know exactly how to make sense of this in any kind of like intuitive way, but I guess it's a formal result. We'll just go along with it. And then if you flip them around, you get the B part on the left and the A part, or A prime, on the right. So anyway, I'm not sure how to explain this such that it has sort of a natural feeling, but it's a technical result, and we'll just go ahead and prove it. And in fact, I'm not going to do most of the proof because the book already gives the proof, and it's a fairly straightforward proof. I think you do a lot of the things that you would kind of expect, which is that you turn it into the expected value, and then you kind of like manipulate some matrix products and transposes with some distribution and so on. So I'm not going to bother to go through that. I mean, I guess if anybody leaves a comment and makes a request on going through that, I'll consider it. But I think really there's one part that is worth talking about because it's not so obvious. And it is the fact that the author in the proof makes the assumption that the expected value of the two variables is both the zero vector, right? That all expected values are zero. And the question is, why do they get to do this, right? That sounds like a fairly heavy-handed assumption to impose, and so you're not really proving it in general. But I'm going to go ahead and explain how, with what it is proved in the book, then the complete proof is actually not too hard, or at least you can kind of see how it goes here. So let's now assume that the expected values are gamma and mu, where these need not necessarily be zero. But a common trick, right? Often what you'll do is sort of like normalize your object in some sense. For us, a nice way, like a nice sense in which we can normalize the vector w is to actually take w minus gamma. Now, this isn't the same thing as w, of course, so it's a new vector w2, but the promise is that we can use what the book has proved and apply it to w2, and then once we have that result, we can somehow relate w2 back to w in a nice, quick, and natural way. And then likewise, we'll define y2 as vector y minus mu. And so anyway, so the important point here is that we have now constructed two vectors for which their expected values are equal to zero, and therefore what the book proved takes care of these cases, right? So from this right here, we can say that if we do matrix A times W2 plus matrix B times Y2, then the result in the book holds. And this is essentially the result of what the book proved applied to W2 and to Y2. And then the claim is, well, look, what is W2, right? W2 just is the same thing as W minus gamma. So the covariance of W2 should be equal to the covariance of just W, and that's because, essentially the covariance in this case, right, like adding a constant will not change the covariance, right? So I'll leave it to the viewer to kind of think about why that is, that like adding this constant vector doesn't change the covariance. But I'm going to take it for the, use this fact for the rest of the video that the covariance of W2 is in fact the same thing as the covariance of W, the covariance of Y2 is the same as the covariance of Y, and so on. So, so ultimately we get that this thing is equal to this thing, but also we can expand it in this other way so that we get toward talking about the covariance of AW plus BY, right? Because like ultimately, right, what we're trying to show in this proof is we're trying to show that this covariance here is equal to this covariance here, right? We're trying to show the equality of these two things. So there's kind of, two lines of calculation here. This one is by sort of expanding out what W2 and Y2 are, distributing out the matrices, using the fact that the covariance is just going to eliminate constant vectors. So that's one line of computation getting us to here. The other line of computation is down here, which I've already talked through. Since all of these things are equal, then we get exactly the equality that we were looking for, which is the equality of these two things. And that concludes the general version of the proof.